So last time we walked through how to debug not a number, um, and now we've got we left this little tweak in here to look at just what's happening to box 0, so we can kind of focus in on one situation. So now let's clean this up and see what's going on with this crazy looking graph here. Okay. Um, So just remember that we've said it's a hard-coded 0 here. We're going to want to unhard-code this. But notice that this is pretty fuzzy. It's like it's taking huge steps. Like it's not really converging on one thing. I mean, it's kind of converged in a sense, but it's definitely like flailing around a lot. Do you see it? You've probably been saying, "Prof, why don't you fix this right now? Come on, haven't you seen it?" Well, what are we seeing? There are two elements of gradient descent. We figure out what the gradient is, and then we take a step in that direction. How big of a step? So effectively here, we're taking a step of the full way in the gradient. Like, hello, we should make a small step. Oh, nope, we're going all the way there, going all in, and maybe we went too far. So I put it as a learning rate of 1. Yeah, that's our problem. So maybe we should be a little more conservative. We only saw 10 beads after all. If we'd seen like 1,000 beads each time. Well, okay, it's hard to tell because we look at this dynamic range here. Let me just change the y limits here so we can see what the difference is. So let's start from like we want a loss of like 1 to 1.5 maybe. Let's look at that. So that's all in there. So doesn't that look so much better all of a sudden? And then we'll do 10 back to 10 beads each time. And yeah, on that same scale, well, we were off the scale on that one. So clearly, if we were doing 1,000 beads each time, then we're still going to be fuzzy. But this a learning rate of 1 would have been fine if our batch size is huge. So let's actually name this. This is a batch size. So we were running with a batch size of 1,000, and a batch size of 1,000 lets us have a pretty small variance in the loss batch to batch, even at a learning rate of 1. Learning rate 1.0. But could we? So 1,000 beads each round. That's kind of a lot to see each time, and in this simple example, that's fine. But how could we make it work with our original batch size of 10? Well, maybe we could do a smaller learning rate. Instead of 1.0, which is when e 0, 10 to the 0th is 1, we could do 1e minus 1. Let's try that, see if that tames down our variance here. Let me tweak the y limits a little bit so we can see 0.8 to 1.5 maybe. Okay, so I'll just do that contrast again. So we had from learning rate of 1 is massive big variance, learning rate of 0.1 tames it down, so we're making smaller steps. Learning rate of 0.01, 10 to the negative 2. Okay, that's already smaller. Learning rate of 10 to the negative 3. Okay, pretty good. 10 to the negative 4. And there's still some variance in there, but we're taming it down a lot. One thing we're not seeing in here is the fundamental variance in the loss that's just based on each individual batch. So we'd have to zoom in a little more to see that. Let me comment out our y limits. So we should be able to see, maybe if I use a fewer iterations, we'll start to see this. Yeah, like this is still, it's converging to closer to the right answer, but its variance is increasing because as it gets closer, the chance that somehow we'll occasionally get just to those minority, the smaller counts gets larger. This is maybe a more subtle issue, but we've got basically the right thing here. So we've determined that as our uh, I'll plot the whole thing here again. So this is back on our original scale. As our batch size gets lower, our learning rate should also get lower so that we don't overly take into account information from any one particular batch. Okay, so this looks like it's pretty good for box 0. So we've converged on 0.34, 0.33, and 0.31. Maybe that's a little bit too small of a learning rate. Maybe we should actually um, do a little bit more. Okay, so we're a little better here. This is also still kind of a small batch size, but we should be able to still learn effectively with this. And we're close to right. This is definitely more close to our true number. But notice that we've only done box 0. So box 1 is still this 0.3, 0.3, 0.3. I'll put it back to pick box and turn off our Y limit here because I want to show you something that happens here. Run. What is that? So it looks like we've got two different things going on here. Like there's this top pattern here, which is what we saw before, and then there's this bottom pattern here. Let me go back to a manual choice, but this time I'm going to pick box 1. Yeah, that looks like what we saw on the bottom here. Okay, so in box 1, remember box 1 was the one that was really imbalanced. It had so much of the orange beads and a little bit of red and a little bit of yellow. So we are eventually starting to learn that real probability. In fact, what was our true distribution here? Maybe what I should do is take the true distribution and put it down here. This is a nice situation where we actually know what the correct answer is, so we can keep comparing things to the correct answer. Most of the time we don't know what the correct answer is. So this is why we get to explore it in this little constrained situation. So we've got 0.06, 0.86, and 0.06. So are we learning that? Well, we're sort of moving in that direction. We're not quite there yet. Maybe this learning rate isn't as appropriate for this task. Maybe certainly we needed a larger batch because there's still some possibility that we're going to see all 10 from in a group of 10 beads. There's still a possibility that we might see very few of these actual orange beads that were the most highly represented in general. So we do a higher batch size. Yeah, now that's still generally dropping down. It's not as likely to get a huge spike of loss. So maybe a larger batch size works better for this. Now let's put on the first box again. So we increased the batch size and we got a smoother learning for box 1, but putting back in box 0, that put us back weird again. Maybe this is a plotting artifact. So we saw something going on for box 1 where we traced this lower part of the line, and something going on for box 0. We had a pretty flat, like a little bit lower. It went down a little bit and then flattened out a lot. So what we're seeing is the plot going back and forth between these two situations, depending on which box we picked. So sometimes you want to plot your losses smooth, but sometimes we want to just do dots. So now if we don't connect them, you see there's actually none of those weird losses in the middle. That was just an artifact of trying to connect all the adjacent points. So always be careful with plotting, that you're not that what you're seeing isn't just an artifact of how you're plotting things. So it looks like here um, that one box, so box 0, had this behavior on the top, and one box, box 1, had this behavior down here. So this is kind of what we mean by um, something is easier or harder in general. It's harder to guess box 0. Uh, Box 0 is ambiguous. We don't know what bead we're going to get. Box 1, we can do a much better job at guessing because we'll be able to guess that orange bead. So our loss overall is going down here. We're being able to make better and better guesses at this box. We can really see this clearly if we crank up the batch size. So now we have these nice smooth estimates. So it looks like this this lower bound here is converging to something. Like there's going to be some loss that's not 0, but kind of some fundamental difficulty score of how hard this box is. I won't get into it for this lab, but if you're mathematically inclined, or if you like information theory, or if you're an electrical engineer and you think about these things, there's a reason this loss is called cross entropy, um, because it's measuring the difference in entropy of the distribution that we're guessing versus the true distribution. So these lines are both mutually going to converge to the entropies of the true distribution. Um, so I think we have successfully debugged our code, and we now have a plot that, or we now have a training loop that uses stochastic gradient descent to learn proportions, and we've found that it reasonably correctly learns the correct proportions for the top box and the bottom box. It hasn't yet converged. Maybe we need more than 5,000 iterations. So it actually kind of needs a lot. Choose 50,000 iterations to learn even a simple proportion. There are more efficient algorithms here, um, and we're already doing pretty well. But we'll see that yeah, now that we've gone out a little bit farther, now we can see that it does seem like we've converged here on both of them, and we've gotten to something that's quite close to the true distributions. It just took a while. So later you might learn about more efficient algorithms for this. Maybe we'd wanted to adapt the learning rate somehow because this wasn't a ideal learning rate overall. But we've seen how this is a pretty reasonable learning rate, and it got even these two different boxes to learn reasonably well. So as a little exercise for yourself, try going back through what we did here on your own and try hitting all these mistakes yourself. Try recognizing what does it look like when you've got your loss wrong, when you're stepping in the wrong direction. What does it look like when you're about to hit a not a number or an infinite? You're about to have something that blows up. Um, how do you keep track of when you've defined functions in different places? How do you make sure that you're uh, running the right code and editing the right code? So just take advantage of this as a little constrained practice that you know what the right answer is. Work through it, get some practice with this, and it'll serve you well when you start doing numerical computing and the things are just complicated and so big and so many different lines of code. You'll have some of this experience to build on. To say, well, this is kind of what that looked like, and this is what I did. So remember your restart and run all. So start from a clean slate and try again. Um, remember to accurately trace back your debugging. Say, what did I actually need to change? Um, or what was the problem? What led me there? Remember iterative development. Instead of thinking everything through all the time, try stuff. Um, try it in a temporary cell somewhere, um, and actually look at the data values that you're getting. Um, and notice the value of these assert statements. These simple little checks at the beginning let us quickly catch our most egregious obvious error well before it affected any of the rest of our learning. So it'd be a good idea to just sprinkle around in your code assertions of things that should obviously be true. Just check it. And then when something breaks, you get an alert early. You don't have to go tracing through a whole bunch of spaghetti code and um, through multiple steps of numerical computation. You got that assertion failure right there. You've got the case that failed, and then you can debug it right there. So hopefully this kind of little exercise will do you well in your future of scientific computing, machine learning, and everything else that we do. All right, and we'll end it here.